In this video, we're going to be looking at factors that affect solubility. In particular, we're going to be looking at nature of substance, temperature, and pressure. Substances have differing abilities to dissolve in water. Some dissolve well, while others won't dissolve at all. Solubility is defined as a solute's ability to dissolve in water. A substance that is very soluble dissolves well, and an insoluble substance does not and tends to form a precipitate. A precipitate is a solid that will form at the bottom of your solution. Number 1, the nature of the substance. Solubility of ionic substances, or salts. Remember that when we've talked about ionic substances, another name for ionic is a salt. A salt is dissolvable if it easily dissociates into ions. What I mean by dissociates into ions is that it will easily break apart into its separate charges. Soluble salts dissolve well because they easily break apart into ions when polar water molecules pull the ions apart. If you go ahead and look to the right of your screen, you will see an example of this. Here we have a crystal of sodium chloride. As you can see, the water molecules will surround the different ions and pull them away from the crystal of sodium chloride. If you look at the top, we have a saturated sodium ion. We know that a sodium ion has a positive charge, and water molecules are a polar substance. So notice that the negative end of the water molecule surrounds the positive sodium ion, while down below we have a chloride ion, and that has a negative charge, and the positive side of water molecules is pointing towards that ion. Insoluble salts do not break apart into ions, and that's because the ionic bonds are very, very strong, and that they're so strong that they actually are more attracted to each other than they are to water. So they actually form precipitates. And what we have to determine and to understand whether or not a salt is soluble or insoluble are something called solubility rules. Now here's an example. So we have a chart off to the right-hand side, and what we have are some examples. So what I'm going to do is I'm going to work us through some of these examples so we can figure out how to use our solubility chart. So our question is, will these substances dissolve? And in particular, will they dissolve in water? So we need to remember a few different things. So let's look at the first one. We have lithium bromide. So notice that over here, what we have is we have things that are generally soluble. Alkali ions. So alkali ions are everything that are in the first group of the periodic table. So if you think about where lithium bromide is, and you might want to have a periodic table out in front of you, what you see is lithium is an alkali ion. So what that means is that it is always soluble. So will this dissolve in water? Yes, it will. And that's because lithium bonded with anything will always dissolve in water. Let's go ahead and look at number 2. We have fluorine. So what we want to do is we want to look. Fluorine is not an alkali metal, so we want to look at some of the other negatively charged ions. Well, here's fluorine right here. It is generally soluble, which means it will normally dissolve, except if it's bonded to lead, calcium, barium, strontium, or magnesium. Well, what is it bonded to? It's bonded to lead. So what that means is that this is not soluble. It will not dissolve in water. Number 3, we have sodium hydroxide. Well, if you look at what sodium is, what we see is sodium, again, is an alkali ion. So what that means is that it will dissolve. Let's look at number 4. We have calcium hydroxide. Well, we actually don't have anything too much about calcium. We see calcium right here, but we do have things that are generally insoluble. So here's my hydroxides. These are generally insoluble, and they're insoluble except for calcium, barium, strontium, alkali ions, and our ammonia. So actually, this right here is actually soluble because it's insoluble except when bonded to that. And since it is bonded to calcium, it is soluble. Let's go ahead and look at number 5. Here we have ammonium carbonate. So here we have some information about carbonates. Generally, they are insoluble, and they are insoluble except when they are bonded to alkali metals and our ammonium ion, and it is bonded to ammonium ion, so that substance is soluble. But what about barium carbonate? Well, it's not one of the exceptions, which means that this must be insoluble, so it will not dissolve. So those are your solubility rules, and that's how you would use them. This chart becomes very handy, and you want to be able to have this near you when you are talking about these. Covalent substances. So we just talked about ionic substances. If we want to figure out if ionic substances will dissolve, we need a solubility chart. However, with covalent substances, what we want to think about is polarity. And we want to think about this idea of like dissolves like. And what that means is that polar compounds is a compound that has that uneven distribution of charge, and we've actually looked at this especially when we've looked at molecular geometry. And non-polar compounds has charges that are relatively evenly distributed throughout the molecule. So liquids mixed well are said to be miscible. If liquids are immiscible, they form layers. So let's go ahead and look at this chart right here and kind of identify this like dissolves like. What we have is we have a polar solvent and a polar solute. It will be soluble. If they're both nonpolar, it will be soluble as well. However, if they are not alike, so here we have them not alike, they are not soluble, so they will not dissolve. So you need to know what is the polarity of the solute and what is the polarity of the solvent. If they are soluble and we have two liquids, we say that they are miscible. Two liquids that are immiscible, they form layers. Now, when you think about that idea of immiscible, I like to think of the idea of if you've ever mixed like oil and vinegar when you've had a salad dressing. If you let that sit, what you see is that you have a layer of oil on top and the vinegar at the bottom. Those are immiscible. If you shake it up, they will mix for a little bit, but they quickly separate into their two different layers. Let's go ahead and talk about temperature. Temperature is a huge factor with solubility. So, solid solutes. Let's think about some sodium chloride or table salt and think about how it dissolves. If we increase the temperature, we generally increase the solubility of a substance. When we decrease the temperature, we decrease the solubility. If you've ever had to dissolve salt into water, if you want to dissolve more salt into the water, you can actually do that by heating up the water before you start dissolving the salt into there. So by increasing the temperature, we're able to increase the solubility. However, if we think of gas, it's actually the opposite. So we're going to think of carbon dioxide. And carbon dioxide is like the carbonation that you would have in your soda. Now, if we increase the temperature, we actually decrease the solubility of gas particles. Go ahead and think about your kinetic molecular theory. What happens when we increase the temperature? Well, if we increase the temperature of gas, they start to move faster. Well, if it's a gas particle, what happens is they start to move faster and they have enough energy where they can actually leave the liquid of the substance. Where if we decrease the temperature, we increase the solubility. So if you have a soda and you have it cold and you have it at room temperature, and you want one to have more carbonation, you're going to want to have the one at lower temperatures because the carbonation will remain dissolved at a lower temperature than it will at the higher temperature. So here what we have is we have a solubility curve. These are actually really helpful, and we're going to be doing a couple of different problems with these. But before we move on, let's go ahead and identify some key parts of the solubility curve. One of the first things that we want to pay attention to is we want to pay attention to our axes. So notice that we have temperature down here because, as we just said, solubility is temperature dependent. It will change depending on the temperature of the substance. And as you can see, most of these are probably solid because as we increase the temperature, we're increasing the solubility. Which one of these might be gases? Well, you want to look for something that's actually decreasing with temperature. So here we have ammonium and we have sulfur dioxide. So notice that those are decreasing solubility as we increase temperature, just like gases do. On here, we have solute per 100 grams of water. So what we can say is we can identify how much of a substance will dissolve in 100 grams of water at a given temperature. So let's look at a pretty straightforward one. Let's look at sodium nitrate. So if we were at 40 degrees Celsius and we wanted to know how much we could dissolve in 100 grams of water, we could read this all the way up and we could estimate, we could say maybe about 105 grams would dissolve in 100 grams of water. So what we're going to do is we're going to go ahead and we're going to switch screens and we're going to solve these two problems using the solubility graph and some of our math tools. So what we have here is we have a solubility curve and we're going to solve a couple different solubility problems. So let's take a look at the first problem. So it says how many grams of potassium nitrate can be dissolved in 300 grams of water at 50 degrees Celsius. Now, a couple things I want to point out. It's really important that they identify what substance we're talking about because as you can see, each substance has a different line. And in particular, we're going to be paying attention to this one line right here. So that's really important. The other part that's important that is not going to be in our problem but helps us get a data point is the 50 degrees. And the reason why is because we're going to be reading a point at 50 degrees Celsius. Now, what we're going to be doing to set up this problem is we're going to be setting up some inequalities. So when we think about solubility, solubility is often referenced by grams of solute over 100 grams of water. And actually you can see that right here because as you can see, the solubility right here is solute per 100 grams of water. So we're going to set up some ratio to solve for this problem. So we want to know how many grams. So we don't know the top. We don't know that. So I'm going to put X grams of KNO3. And we want to know how much is dissolved in 300 grams of water. So my 300 grams of water is going to go at the bottom. And then I'm going to set it equal to the solubility of that substance at 50 degrees Celsius. So if I go up and I take my 50 degrees and I read all the way up to here, I'm going to say that's approximately 83 grams of potassium nitrate per 100 grams of water. Now what I can do is I could actually cross multiply and I could solve for X. So I'm going to show all my work. So I'm going to have X grams of potassium nitrate times 100 grams of, oops, this is not potassium nitrate. That's my bad. Let's go ahead and fix that. That's of water. Equals 300 grams of water times 83 grams of potassium nitrate. Divide this by my 100 grams of water. 100 grams of water. And I'm going to take my 300 and multiply it by 83 and then divide by 100. And what that ends up being is it ends up being 249 grams of potassium nitrate. However, my problem, we have 83 grams. We're going to assume that this has a decimal. Let's assume this is exact. So I'm going to round this actually up to 3 significant figures and say 350 grams of potassium nitrate. So I'm going to say 300. 250 grams of potassium nitrate. So that's the first one. Now the second one says if this solution, and the solution that they're talking about is a 300 grams of water. So they're talking about this solution that we just solved for. If this solution is cooled to 10 degrees Celsius, how many grams of potassium nitrate will precipitate out of the solution? So what we're thinking about is when we cool the substance, not as much potassium nitrate will be able to dissolve. And when it is not able to dissolve, what's going to happen is going to form a precipitate, which means it's going to come out of solution, it's going to fall to the bottom of, say, the flask or the beaker, and it's going to be a solid. So we want to know how much is going to form a solid at the bottom when we cool it to 10 degrees Celsius. So the first thing that we're going to do is we're actually going to solve the exact same problem, but instead of having this right here, we're going to do it for 10 degrees Celsius. So I'm going to go ahead and do the second problem in a slightly different color so we can kind of see the difference. So we still want to know how many grams of potassium nitrate at 300 grams of water. But remember, this is at 10 degrees Celsius now. So I want to know how much will dissolve. So now I need to Scroll back up here. Here's my line. A lot less can dissolve. So we're going to look right here. And I'm going to say that's about 23 grams. So we're going to say 23 grams of potassium nitrate will dissolve in 100 grams of water. We're going to go ahead and do some cross multiplication like we did before. So I'm going to have X grams of potassium nitrate times 100 grams of water. And that's going to be equal to 23 grams of potassium nitrate times 300 grams of water. And then divide that by my 100 grams of water. Of water. And what we get is that 69 grams of potassium nitrate, grams of potassium nitrate can dissolve. So if we think about that, that's how much can dissolve. What we originally had in there was 250 grams. So how much will actually precipitate out? Well, 250 grams minus 69 grams is going to be 181 grams. So that's how much will precipitate out. So I'm going to put PPT for precipitate. So that's how much will precipitate out of solution. And so those are working with the solubility curve problems. The last factor that affects solubility is pressure, and this really only applies to gases. And for this, we actually have a rule of thumb. And we have this idea called Henry's law, and it is P equals K times C. So first, let's identify what our variables are. P is the partial pressure of the gas above the solution, and that's going to be in atmosphere. So how much pressure is it experiencing? C is the concentration of dissolved gas, and this is going to have units of moles over liters. So we can replace C with moles over liters. And K is a constant, and it really depends on the substance being dissolved. So if we're talking about bromine, they would all have the exact same K because we're talking about the same substance. The concentration of dissolved gas is directly related to the partial pressure of the gas above the solution. What that means is that the higher the partial pressure for the gas above the solution, the more soluble the gas will be. Again, I like to think of the idea of a soda. If you have a soda or a can under pressure, there is a lot more gas that can be dissolved, and they actually have it in a can so that we can actually keep the carbonation in there. However, the moment that you open the can, what you know is that you hear that hiss because all of a sudden you are decreasing the pressure and it can't hold all that gas in this soda anymore, so a bunch of carbonation escapes. So let's go ahead and use this law to solve this problem right here. All right, what we have here is we have a problem that's going to allow us to use Henry's law to figure out how much of a gas can be dissolved in a liquid at a certain pressure. So we have at 0.750 atmospheres and 25 degrees Celsius, 3.36 times 10 to the negative 3 grams of nitrogen can dissolve in 0.250 liters of water. And the first question is asking us, what is the value of the Henry's law constant, which is K? So let's go ahead and remind ourselves about the equation. So our equation says P, which is the pressure, is equal to K, which is a constant, times C, which is concentration. Now for our cases right now, I'm going to go ahead and I'm going to replace C with moles over liters because those are the units that we have. So if we look at our problem, we identify what we're given. We are given that pressure equals 0.750 atmospheres. We don't know what K is. That's what we're trying to solve for. We are given 3.36 times 10 to the negative 3 grams of nitrogen, and we're actually going to be able to convert that into moles. So that's going to be our moles on top of here. And we also know liters, which is 0.250 liters. So we want to solve for K. So what I'm going to do is I'm going to multiply both sides by liters over moles to cancel out my, liters, moles, moles. So we're going to over here is liters divided by moles. So before I can plug anything in, the first thing I need to do is be able to convert my grams into moles, and we're going to be using our molar mass of nitrogen. So I'm going to actually put this kind of off to the side over here. I'm going to have 3.36 times 10 to the negative 3 grams. I'm going to have my molar mass of nitrogen. My molar mass is 28.014 grams of nitrogen over 1 mole of nitrogen. Cancel out my grams, and what I end up getting for my moles is 1.20 times 10 to the negative 4th moles. So that's what I'm going to be able to plug in over here. So now let's go ahead and plug in all of my values. I'm going to go ahead and use red. So we have liters, which is 0.250 liters, times my pressure, which I have a 0.750 atmospheres. And then I'm going to divide it by my number of moles, 1.20 times 10 to the negative 4th moles. And this is going to equal K. And my K ends up being, it's kind of a big number, 1560. And what are its units? Well, its units are liters, atmospheres, and moles. So I'm going to have liters times atmospheres divided by moles. And so this is the K for nitrogen at this temperature. So now our next problem says, how many moles of nitrogen can dissolve in 0.500 liters of water at 1 atmosphere in pressure? So what we have is we have a slightly different problem. So let's identify what's given. So here are our givens. And we are given, well, we know K because we actually already solved for that. So 1560 liters atmospheres times or over moles. We are given our volume or liters. I'm going to put L or V depending on what you want to put. And it is 0.500 liters. And then I'm also given my pressure, which is 1.00 atmospheres. What I'm trying to solve for is my number of moles. So if we go back to my problem, so my original problem is pressure equals K, and then remember we're replacing that, moles times a liter. And what I'm trying to solve for is this right here. So I'm going to multiply both sides by liters. That cancels out, and then I'm going to divide by K. Divide by K. And that'll get me moles by myself. So let's go ahead and plug things in. I have my liters, which is 0.500 liters. My pressure, which is 1.00 atmospheres. And then my constant, which is 1560 liters times atmospheres over a mole. If you notice, my units cancel out, and I'm left with the units of moles. And if I calculate that out, I will get 3.21 times 10 to the negative 4th moles. So if we compare that, what we see is that we are able to dissolve more gas because we're at a higher pressure. So that is the last problem that we have for this video. So we've gone through our factors that affect solubility, and you guys have learned how to calculate problems using a solubility graph, and now you're able to use Henry's law.